Today we're doing scale drawings and models. A scale drawing or a model is just used to represent an object that is too large or too small to be built at actual size. You can think of an example like a map. Okay? It's a paper representation of a state or city or even the country, right? Too big to put the whole thing, the actual size on paper, right? So what they do is they scale it. They have a scale. Which, if you've ever looked at a map before, you can see like it usually says like 1 inch is 100 miles, or 1 inch is 300 miles. It just depends on the size of the map and that kind of thing. But also goes for things that are too small to be built at actual size. Examples such as like protons and neutrons and atoms and those kind of things. Things we can't see with our own eye and things we can't even see with a regular microscope. Okay? What they've done is they've made models to represent so you can see the details and all those things that you wouldn't be able to see normally. Scale, when we talk about scale, it's determined by a ratio of a given length on the model to its corresponding length on the actual object. A scale such as 1 inch is equal to 3 feet. There's all kinds of different scales, such as like when architects design buildings, they have a scale like a scale model of different things, right? So then the engineers and the people, the construction workers, can make the actual room based off of a model, but they have to know the scale. This is supposed to be 5 inches in real life when it's 1 inch. Or it could be things that go from larger or small to large, like 1 centimeter is actually 2 millimeters, like a smaller object. If let's think of like an ant. An ant's not very big. So they blow up a picture of an ant, and now you can see little details, right? So that's what scale drawings and models are useful for. So you're going to see some word problems today, like this one. It says a model of a dragonfly has a wingspan of 4 centimeters. If the length of the insect's actual wing is 6 centimeters, what is the scale? So it's asking what is the scale, and the scale is always a ratio of 1 to a different number. They don't always have to be the same units. We'll talk about later where they are, but in this case, they don't have to be. And here's, I wrote model length over actual length. There's a reason I want it done this way. Scales are always model to actual, and it just helps you keep units together, and also just to keep things organized. So you always do model over actual. So I'm going to write what the model is. What's the wingspan of the model? 4 centimeters, and the actual length is 6 centimeters. And then to do a scale, what I'm going to do is I'm going to set it up with a ratio of proportion, just like we did yesterday, of 1 over a number, 1 over x. I need to figure out how many centimeters the actual length is compared to 1 centimeter of the model. So we just set it up just like this. So I find x by cross multiplying. Getting 4x is equal to 6, which when I divide by 4, I find that x is equal to 1.5 centimeters. But that's not my answer. That is just what x is. My answer is actually what is the scale, which is 1 centimeter to 1.5 centimeters. And you write it like that. The book usually writes it like that, where it's equal to. It doesn't matter how you write it. You just have to write the scale. I'm not going to take 1.5 as the answer. If that's all you circle, I'm not going to take it. When you show your work today on your homework, which is mandatory, you have to actually write the scale. Because 1 inch on the model, or 1 centimeter on the model, is 1.5 centimeters on the actual. So what is the scale? It says pillars are 17 feet tall. The scale has pillars that are 5 inches tall. So the model is 5 inches tall. The actual one is 17 inches tall. So let's do model over actual. The model is 5 inches. The actual is 17 feet. I need to set up a scale, so it's going to be 1 over a number, so 1 over x. I cross multiply solve.
Wait, hold up. No, hold up.
So 5x is equal to 17. Divide by 5. And I find that x is equal to 3.4, which is feet, because we're talking about the actual. My actual's in feet. But that's not my answer. That's just part of it. So I need a scale that is 1 inch to 3.4 feet. That would be my answer. If the scale drawing and the model have the same unit measure, then we can write the scale without the units. We've been writing the scale with the units, such as the problem 4 where it was 1 inch was 3.4 feet. That would be necessary. Those units would be necessary because you wouldn't want a model that was 1 inch tall and then make the actual building 3.4 inches tall. That just wouldn't make sense for when you're trying to build the actual building, right? So units are important unless they have the same unit, and then it's not really necessary. And we can write them without the units, and that's what we call the scale factor. They're going to give you a few problems that's asked for scale factor, which is what you need to do here. 1 inch equals 2 feet. I need to change this to a scale factor, which means they need to have the same unit. So first thing I write what they give me. 1 inch equals 2 feet. And then I change the units to the same. Which units do we want to go to?
Inches.
Inches. You usually want to go to the smaller unit. It's easier to work with. So I'm going to take 2 feet. I'm going to times it by 12 inches because there are 12 inches in a foot. Which the conversion rate is something we've practiced. All right, something we learned on Monday. Feet cancel. The only unit I have left is inches, which is what I want. 2 times 12 is 24. So I could write the scale factor as 1 over 24. Find the scale factor. What that means is you need to find the scale that is 1 over a number that when they have the same units. You need to get rid of the units. And then also it needs to be 1 on top. So I'm going to go 4 inches over 5 feet. I need to change to a smaller unit, so I'm going to take 5 feet times 12 inches, which the conversion rate is 12 inches to 1 foot. Right? Just like we did on Monday, we cancel feet. 5 times 12 is 60. But my scale factor is not 6 over 40. I can't just stop there. What I got to do is I got to reduce it. I want 1 on top. So I divide both of these by 4. And I get 1 over 15. And that would be my scale factor. 2 centimeters equals 10 meters. So I need to change them to the same unit. I'm going to change both of them to centimeters. I'm going to change the bottom one to centimeters. And I know that there are 100 centimeters in 1 meter. Well, meters cancel. I take 10 times 100, which gives me 1,000. But I can't just leave it as 2 over 1,000. I need scales always have 1 on top. So I need to divide both these by 2. And when you do that, you get 1 over 500. So the problem says a map shows the room that is 7.25 inches. So a map gave me a room that's 7 1/4 inches. They might write this as 7 and 1 over 4 in a fraction. Easiest thing to do is just change it to a decimal, which here they give you, but you'll see several problems where they don't. Easiest thing to do is change it in a decimal. If the scale is 1 inch is equal to 8 feet, then you need to find the width of the actual room. So what I do is I go model over actual. First thing I do is I write the scale they give me, which is 1 inch is equal to 8 feet. 1 inch on the model is 8 feet in real life. And then what I'm going to do is I look to see what do they give me. Do they give me the model length or do they give me the actual length? They gave me the model length. They said the map is a room that's 7.25 inches. I know that's the model because that's the units they're using for the model is inches. So 7.25 would go here. And what they're asking is what is the width of the actual room? So that would be my x. Now, I just cross multiply solve. Which 1x I can just write as x. Which 8 times 7.25 is 58. And I don't have to do any division because it's 1x, which is the same thing as x. And make sure you have your unit, which the actual is in feet. So the width of the actual room is 58 feet long.
Yeah, baby.
Here's your assignment for today.
You got a lot of time left.